Yasuhiro Mori, and the person who sent you the emails to invite you to this workshop. And as all of you know, our main guest, Professor Cornell, is one of the pioneers in structural reliability, and of course, still very active in this field, and especially in the statistical reliability. This time, Professor Nakashima of the EPRI is still here. He invited Professor Cornell for the meeting of the AIJ working group of steel structures, and taking advantage of this opportunity, Professor Takuya Nagae here and myself organized this workshop for young researchers and engineers in Japan who are interested in reliability-based seismic design in order to discuss its future.
I would like to give my thanks and appreciation for the invitation to appear here and the opportunity to speak to you, and also the opportunity to visit Japan again, which is a place I enjoy coming often. And we'll begin by changing the title. As Yasuhiro knows, shortly after I sent him the previous title, my old computer crashed. I lost the email and a few other things. So I reconstructed the title as closely as I could remember, remembering that the subject is this question of record selection, in particular for use in nonlinear time history analysis in the development of probability-based criteria in buildings. Get this a little bit closer so I don't walk through the big. Better stand on the side.
So do I can get the screen up here to this helpful selection. Yeah.
This framework is made up of several pieces. Four basic sets of variables. At the beginning is something we call an intensity measure. It's useful to think of that as peak ground acceleration or spectral acceleration. But it's a measure of the intensity of shaking. And that's characterized by some function that's the annual likelihood of exceeding that intensity. A second set of variables that we call engineering demand parameters. Traditionally, those might be something like the maximum interstory drift in a frame. From a structural point of view, we're interested, from a probabilistic point of view, we're interested in characterizing the probability, the conditional probability of seeing some level of, say, drift in the structure, given the intensity of the earthquake. And we can put those together, as you know, to get the likelihood, annual likelihood of displacement, for example. In the other parts of the program, people are also interested in trying to predict damage to the facility given the displacements. So that might be the degree of cracking in a partition. And from the degrees of damage, the next step is to try to predict what we call decision variables. And that might be the repair cost for those particular partitions, for example, given their damage state. So these several elements of the structure of the analysis problem associated with performance-based design are put together in a triple integral, which is called the framework equation. And as probabilists, you'll recognize this as something like this mean frequency density, annual frequency of exceeding a particular ground motion level, a conditional distribution of displacement given ground motion, a conditional distribution of damage given displacement, and a conditional distribution of, for example, dollars given damage. So this ultimately, we're interested in these so-called decision variables, which might be dollar loss, lives, limit state exceedances or not. So for example, this might be something like the mean rate of collapse events. One element of this formulation from a probabilistic point of view is that we use a Markovian type of dependence. For example, we assume here this is a conditional distribution of displacement given intensity measure. This is damage given displacement. You notice it's no longer conditional upon intensity measure. So a simplifying assumption of this Markovian type dependence is used so that the focus of the individual groups in the projects can be to look at damage given displacements without having to worry about what was the intensity or nature of the ground motion which caused it. Or people worried about economic impacts of a given level of damage don't need to worry about structural displacements or intensity measures in the background. And that's a simplifying assumption that helps us enormously. One of the objectives of using this formulation is to develop probabilistic-based codes. Codes that look to the user, engineer user, something like a load and resistance factor formulation. And that goes through a couple of steps. I'll just characterize briefly. This is a somewhat one reduced integral version of the same equation, intensity to engineering demand to a decision variable. The decision variable we were thinking about here that we'd like to have an annual rate of, mean annual rate of, would be a limit state such as collapse, no collapse. So the value z equals 1 might be the collapse condition. The value z equals 0, non-collapse. We can simplify this to more, represent this in variables that are maybe more familiar to us. If we use as an intensity variable, say the spectral acceleration, the intensity of the ground motion shaking as characterized by the spectral acceleration, most likely, or most frequently, we would use spectral acceleration at the first mode natural period of that structure as being the spectral acceleration that best characterizes the frequency content driving the major dynamic response of the structure. This EDP to IM relationship might more specifically be, as I suggested, say the maximum interstory drift, peak drift during time, maximized over all of the stories to get a reflection of the degree of damage in the structure, and its proximity to a collapse condition. So we need to know a conditional distribution of displacements given the strength of the ground motion. We'll get that from nonlinear time history dynamic analysis, or in more approximate schemes by, for example, static methods. Finally, we need a capacity that will tell us the likelihood we get into this limit state given that we have a particular displacement demand. And that capacity would be a capacity measured in displacement terms. And we'll look at some examples of that later. But this becomes now a double integral that captures in the usual sort of reliability context the likelihood of this limit state. Under certain simplifying functional assumptions about these distribution types, for example, that this so-called hazard curve in spectral acceleration takes on basically a power form or Pareto form. If these conditional distributions of displacement given intensity are log normal, this capacity is log normal, this probability in this integral can be solved analytically to a form that I don't want to go into detail. It's simply it's a hazard curve. This probability of collapse becomes the hazard curve evaluated at the displacement capacity measured in spectral acceleration terms. There are a couple of betas, or beta now refers to the standard deviation of the logarithm of capacity or the standard deviation of the logarithm of displacement given spectral acceleration, and some coefficients that come out of slopes of hazard curves, slopes of displacement measures. But the point is it is a rather convenient analytical form, and the test of safety would be then, is this calculated failure probability less than some acceptable target level? But the more interesting form to get this into more viable application terms is to put this into something like a load and resistance factor format. That is, where the engineer compares a capacity, a median capacity in displacement terms, versus multiplied by some kind of reduction factor, like 0.9, like a phi factor. He compares it with the demand, where the demand would be a displacement demand, and it's a median displacement demand under a ground motion, as measured by spectral acceleration, associated with the target failure probability. So, for example, in the steel guidelines called FEMA 350 for steel moment frames, this target failure probability is set at 2% at 50 years, approximately 1 upon 2,500, or 0.0004 per annum. And so we can see how that will work in just a moment. One looks at the ground motion level. For that ground motion level, in fact, looks at the probability, gets a corresponding ground motion level, estimates the corresponding median displacement, and then multiplies it by a gamma factor, some additional factor to reflect other components of uncertainty. So, for example, this phi factor turns out to be an exponential form involving this dispersion, the degree of variability as measured by a standard deviation of log capacity squared. A coefficient k and b, this is a relation, has a sense of slope on the ground motion hazard curve, and b, we'll see a bit later, is a measure of the dependence of displacement upon ground motion intensity. The important thing to recognize here is that with some steps and some analytical assumptions, we've reduced this target limit state probability exercise to a loaded resistance factor form, which makes it more familiar and more acceptable for application in practice and in codes and guidelines. But that we have explicit analytical forms so that if we begin to make analytical studies to understand the degree of variability and capacity, the degree of variability demands, we have a location in which to insert those variabilities, and we get immediately the dependence that our loads and resistance factors have upon that variability. So the elements of this problem then become a hazard curve. This is a probabilistic, a result of probabilistic seismic hazard analysis. This is an annual probability of exceedance as a function of a ground motion intensity measure here, as suggested, spectral acceleration at first mode natural period. Later in the talk, we'll talk about some alternatives for this that may work a little better. This is a measure, a degree, part of the step of that relationship between intensity measure and EDP, or demand. This doesn't show very well. This is spectral acceleration on this axis and drift, maximum drift angle. The structure here happens to be actually an offshore structure, sort of a braced frame, steel braced frame structure. What we show here is an example of what's called an incremental dynamic analysis. That is, a particular ground motion record was taken and scaled to multiple different levels. And for each level, a nonlinear dynamic analysis was run, and the maximum roof drift, or deck drift in this case, was plotted. So this is a result of some 20 or 25 nonlinear dynamic analyses that shows how the drift increases as the ground motion intensity increases. In blue, which you probably can't see, I apologize, is a conventional static pushover corresponding to this braced frame. You see it goes up, there's a yield plateau, this falls when braces buckle, and levels off at a plateau of 70 or 80%. One of the interesting things that comes out of these kinds of studies is one, this sort of represents a dynamic version of this static pushover, but we're interested in how this increases, obviously linearly in the early phases when the structure is linear. It tends to go to at a softer slope, and when the structure is in the decaying strength condition. And then as this becomes into a plateau, it's basically an elastoplastic system by this time, we did get sort of a straight line, something like a reduced stiffness, equal displacement rule taking place. This is a result of doing the same thing for that structure with multiple, some 30 ground motions. And one of the immediate things that comes out of this observation is the need for statistics. So if your structural engineering friends say we don't need probability and statistics in doing structural analysis for earthquakes, if you show them a plot like this, you can ask them, how are you going to deal with the problem that shows this degree of variability from one record to the next? And so what we have here is, again, the level of ground motion as measured by the spectral acceleration in first mode versus maximum story drift. So at any given level, you have degrees of displacement response that vary by a factor of 10 to 20, depending on which record was used. This is, again, why questions of record selection are non-trivial and important to our problem. The nature of these curves, which we call IDAs, or incremental dynamic analyses, is also, I think, interesting. Among other things, we see them all go up, obviously following a fairly constant pattern when we're in the linear range. Also, the softer slope as the structure begins to go into a force degradation range, followed by different levels of severity of the record in the terms of how rapidly the displacement increases as the ground motion increases. We have those that are very flat, which implies a very severe record. Small changes in ground motion lead to very large changes in displacement. And some records which are quite benign. That is, if you follow this line up, you can see that even at spectral accelerations that are 5, 6, 8 times the yield spectral displacement, the displacement versus input is effectively in the same straight line as one would have if the structure had remained linear. But mostly we see, of course, large increases in displacement. And this has led to a definition of a global instability by looking at the slope of this curve. When this curve becomes virtually flat, it implies, just as with a static instability definition, a small increase in load leads to a very large increase in displacement, something like a definition of instability. But here it's a dynamic measure of the load, the dynamic responses we're looking at. Recall each of these lines is the result of 10 or 20 or 30 nonlinear dynamic analysis, something we can afford to do in the university, if not in practice. The other characteristics of these, so in any case, we look at capacity measures often, and as was done in the FEMA 350 or SAC project for steel frames, by looking at the comparative slope here versus the initial slope here. And in fact, using a rule such as 20%, that is, if this slope has become only 20% of the initial slope, defining that as an effective instability. And where that curve happens, these dots on here, where that 20% rule is reached, is an indication of a capacity point. That is where instability, in effect, has happened. So we can measure the displacement capacity by looking at these data points. And this is a measure of the median and the sigma and the dispersion. Another observation to be made about these curves is they're not necessarily monotonic. That is, you can have cases where as you increase the ground motion, the displacements decrease. I'm sure you've seen that yourselves if you've run nonlinear analysis. So we need statistics. This on log plot is a plot of the median and the plus minus 40 percentile. I think it's about perhaps it's a 90 and a 10 percentile value of the displacement corresponding to a particular ground motion level. And this is the dispersion here we're seeing across this level. So from a curve like this, we get a median displacement given the ground motion intensity and the information needed to develop a probability distribution for the displacement given ground motion. So these are the elements of the problem as we see them. We have, this is a drift axis, this is a probability axis, this is a ground motion intensity axis, say spectral acceleration. So we have denoted here this so-called hazard curve, or ground motion hazard curve, which gives us the probability of exceeding a given level of ground motion. So as I suggested, those criteria in the load and resistance factor format would suggest that you enter this curve with a target failure probability, say 1 in 1,000, 1 in 10,000. Go up until you get the corresponding spectral acceleration, which we call spectral acceleration associated with level P0 probability. Move across until you meet that median curve of displacement as a function of spectral acceleration. From down, it gives you a median capacity associated with this probability level, pardon me, a median demand, displacement demand associated with this displacement level. There's a dispersion, as we saw across those mini curves we saw, in the displacement associated with this ground motion level. And then there's a capacity curve, which is a displacement capacity as measured, for example, for the global instability capacity as we saw it. And reliability is, of course, associated with some combination by the convolution that we saw of this curve and these two curves. This kind of thinking has been put into a set of guidelines, published guidelines for behavior and assessment and post-earthquake assessment and new design of steel moment-resisting frames, a large project called the SAC project, sponsored by the Federal Emergency Management Association. These guidelines are all available on websites for FEMA and will be discussed in tomorrow's meeting. They have been discussed in a variety of articles that have appeared in the Journal of Structural Engineering. As a special journal, there's a new special issue of Earthquake Spectra appearing later this year. Another set of collection of articles on the subject. The key characteristics of these guidelines from our perspective are that they're completely probabilistic. There's a start from probability and work up. So the foundation is entirely probabilistic. They're completely dynamic as opposed to static in nature. They are completely nonlinear as opposed to linear in their basis. They involve this global, checking for this global instability that we discussed a moment ago. Also local collapse modes, such as loss of vertical shear capacity and the connections. They are displacement-based rather than force-based. And they separate, again from a probabilistic context, they separate two types of uncertainty that we refer to with complicated words. Aleatory, which is a Latin word meaning a die, something that one flips. So this is a representation of pure randomness, like the nature of these earthquake records. And the second type of uncertainty, which is a Greek word, epistemic, which has to do with knowledge. So this is the type of uncertainty associated with limited knowledge. For example, the fact that we don't know perfectly how our models work and how to model buildings in severe nonlinear behavior. So we look to Professor Nakashima to continue his tests. If only we could get him to run more than one test of each frame, we could begin to measure some of this epistemic uncertainty in the behavior of steel frames. He promises he will do that if he's given a greater budget. Okay, how does all of this fit? We've seen that these ground motion records play an important role in working with nonlinear time history dynamic analysis. But a continuing question that comes back is, which records should I use? Should it be El Centro 1940 or some other record? Or which records? How many records? What do I do with them when I've got them? Do I need to reflect, for example, the important magnitudes at my site, the important distances between the site and important faults? Is the style of faulting, strike slip versus normal, important? Some people worry on normal faults about whether the records are taken on the hanging wall or the footwall of the fault. The soil type, everybody agrees, is important, but these other issues of what should be done with these records remains a wide open question for which there's all continued discussion. The best practice in the United States today, as conducted by engineering seismologists charged with providing these records to the engineers, are the following steps. They do a probabilistic seismic hazard analysis to get one of the curves of the type we saw at the spectral acceleration associated with a period close to the fundamental mode period. They look at a particular probability level, as we saw, for example, 2% in 50 years, or 1 in 2,500. And they disaggregate that, which is a procedure I'm not going to have time to discuss with you. Basically, it gives you the conditional distribution of the magnitude and distance of the event that caused this level of spectral acceleration. So if this 2% in 50 years at your site is 1G, you would say, given 1G, what was the likely causative event? It's found by a simple Bayes theorem kind of computation. So it's an inversion of the input to the hazard analysis to get out this, what caused the event. This probability distribution is then inspected to say what is the most likely magnitude, or what is the expected magnitude, the mean magnitude, to have been the cause of this severe ground motion. And what is the most likely distance, or most mean expected distance. And that is used to select the set of magnitudes and distances of the records that will be selected to be given to the engineer. Typically a mode or mean of that joint distribution is used, mean magnitude and mean distance, or modal magnitude and modal distance. Then the seismologist tries very hard to find the same faulting style, strike slip, for example, to worry about the soil type, to worry about whether it's hanging wall, foot wall, and to then collect from the catalog of thousands of records available some set of such records that meet these conditions. Say within plus or minus 2.5 magnitude units of the most likely magnitude. Then these records are scaled in some way, such that the spectral acceleration that they have, the typical way would be such that the spectral acceleration that they have coincides with this number chosen up here, say 1G. So the records are scaled back to match that 1G level. This is common practice in our Nuclear Regulatory Commission exercises, the PEER project itself, a variety of procedures and recommendations that are common practice today. A number of questions can be asked about this procedure. Why do we disaggregate spectral acceleration? Maybe we should try to disaggregate the drift, if it's actually the drift of the structure we're interested in. That would require some kind of iterative procedure, but might be very useful. Some suggest that we work with epsilon. Let me not follow that. Why do we use the mean instead of the mode, or the mode instead of the mean? The better idea, instead of picking out one magnitude, would be to pick out a set of magnitudes so that you, for example, represent that frequency distribution of magnitude. Some magnitudes a little bigger than the mean, some magnitudes a little less than the mean, but in the right relative proportions that this disaggregation tells you is important to your site. There are many ways scaling might be done. Many people will try to match the records either individually or in an ensemble way to the design response spectrum. Now, design response spectrum might be what we call the uniform hazard spectrum that's come out of the probabilistic seismic hazard analysis. It might be a code shape, UBC, IBC, one of the design code shapes. Well, as I said, that match may be on average, it may be on a record-by-record basis, trying to match the spectrum in a broad sense, or it may be more locally, as I suggested before. The narrowest way to do that is simply to scale each record so that its spectral acceleration at the first mode period of the structure matches this target value, or that target probability. This implies that you must know something about the structure before you scale the records. Also implies you need to know the level of ground motion you're interested in before you scale the record. It implies if some performance-based codes today have one probability level for collapse considerations, another probability level for immediate occupancy or damage, economic damage. That means you would have to have different scaling of the records for these different conditions. Okay, so this process, at least that's used popularly in the US, in those cases when we do nonlinear time history analysis, is, as I suggested, a very careful selection process that is carefully trying to match the records to the site, and to a limited degree match them to the structure by perhaps scaling the records to that first mode period level. And presumably the reason it's done is because we think it matters. And it matters to what? Well, it matters to the structural response, because we're using these records to, of course, obtain structural response predictions. But as structural engineers, at least in my country, we've done almost nothing to communicate to the seismologist what matters to structural response. So the seismologist is collecting these records without knowing anything about the structure or without the professional knowledge of what matters to structural engineers. So the seismologists have been very prudent. They assume everything matters. They assume the magnitude matters, so they make sure the magnitude matches what is the critical magnitude of the site. They assume the distance matters, so they match the distance of the record to the distance of the site, to the fault, critical fault, etc. They assume the style of faulting matters. So they've been very careful and very prudent about that, but without much consideration about response. So I'd like to begin to explore the problem from the structural response perspective, to look more carefully at this question of what matters in terms of how best to select records. And so I start with a null hypothesis that says nothing matters. It doesn't matter which magnitude you choose this record from, or which distance or style of faulting. Now, why does that position maybe make sense as a starting point? Well, I'm going to assume that we're scaling the records to our target level of spectral acceleration at the first mode period. That's a method of scaling I prefer. It's quite commonly used. So we're actually going to scale the records to this, to match them at this spectral acceleration. Well, why does this become a non-issue if we do this? Well, let's assume our structure is not really a structure, but just a linear oscillator. Clearly, if I scale all the records to the first mode spectral acceleration of the linear oscillator, and then run the records through the oscillator, they're all going to give me back exactly the same spectral acceleration. Every record will do exactly the same thing. So that's, as an initial starting point, it makes some sense to me that if I scale the records this way, the results should be independent of the record. So that's rather obvious to the structural engineer, maybe not to the seismologist, but it is to us. And many of our structures, in some degree or another, act pretty much like a 1 degree of freedom system, and perhaps elastically in the small damage regime. What about linear multi-degree of freedom systems? Well, if we assume a SRSS kind of rule, we in 2 modes, we can separate the estimated response into a participation factor in a first mode, and then a set of factors that represent second mode impact, that is the ratio of participation factors, and a ratio of spectral accelerations at second mode to first mode. That would be sort of our SSRS prediction. But of course, even if we scale to the first mode spectral acceleration, the different records are going to give us different ratios of this second mode to first mode spectral acceleration. So the variability we're going to see record to record, if this is the way the structure behaves, is going to be from this spectral shape issue. And so the question is, how important is this second term? There's some constants that run around in here, but the net effect is, how big is the deviation of the spectral shape away from the average spectral shape? That's what's going to show up in the only term, the really remaining random term, or record-to-record variability. I contend that term is usually fairly small, and so the anticipation that there will not be too much variation from record to record in multi-degree of freedom linear systems is perhaps to be anticipated. Again, supporting this notion that perhaps our results will not be too sensitive to the record selection as long as we do the scaling this way. Well, what about nonlinear systems? Well, we're going to look directly, by making some comparisons in a moment, at nonlinear systems. Both oscillators and some multi-degree of freedom systems. And we'll look at them again directly, and you'll see in a moment what I mean by directly. We'll compare response from different record sets, just to see if it matters. And then we'll look at them indirectly by studying and from a probabilistic or statistical point of view, the dependence of the response on these record properties that the seismologist thinks are important, such as magnitude and distance, multi-step, etc. But conditionally on knowing what the spectral acceleration is. Why do I say that? Because remember, the hypothesis, the starting point is that we scale the records to this level. So all of the records have the same level. The question is, how important is magnitude to response, for example? So that's the conditional dependence or correlation we're looking for. Here's a very busy slide that just explains this little test we're going to do for nonlinear, this direct way of looking at nonlinear oscillators. We'll take a very simple system, 1.5 second period, bilinear. We're going to adjust the strength of the system so that it gives ductilities first of about 2, and then later we'll adjust it so it gives the ductilities about 6. We're going to say that this site of this structure is dominated by magnitude 7s at 20 kilometers. We have one fault at the same distance that only produces one kind of magnitude. And we're going to then estimate what the response is of the displacement by taking a suite of records from exactly that magnitude and distance. So we do as well as a seismologist can by looking at a narrow magnitude bin and a narrow distance bin, common soil type, and that will be called what we call the target record set. So that's precisely matching the conditions that nature is throwing at us. And then we're going to look at some other record sets to see if it matters. And the comparison we're going to make is to take the records, for example, this target set, scale them to the median of that target set, median spectral acceleration, which happens to be 0.17 g. That scaling isn't necessary here, but it reduces dispersion and makes our tests, our significance tests, stronger. So first we're going to get this best available results from our target set, and then we're going to see what happens when we use the wrong set of records. Okay? We'll choose the record some other way to see if it matters compared to the right set of records. So what are the wrong sets of records we're going to use? Well, if the wrong, given that you believe that magnitude and distance and other properties of the record are important, undermine my null hypothesis that they are not important. The best way to select records would be to go to the catalog of records and choose them at random. That's what a statistician would tell you to do. Choose the records at random so you don't throw any bias into the problem by taking records that look smooth or records that just give you low response in some modes where you're building because you like the building to look like it behaves well. Well, the only condition is when we go to the records, when you go to the catalog, is that we have lots of records, but comparatively few events. Comparatively few events are causing those things. So we suggested that we choose the records at random, but subject to the constraint that we avoid repeating events if possible. So instead of having, I'm going to choose a set of 10 records, I don't want 9 records from Loma Prieta and 1 from El Centro. I would like to have 1 from Loma Prieta, 1 from El Centro, and 1 from Taft. I'd like to make different events in that process to avoid potential within-event correlation. So we're going to choose some random, effectively random sets. And here's the results for the sort of low ductility level. The X's here are the results of running this set of records that are very close to magnitude 7 and very close to 20 kilometers. These are some of the 10 records. Notice they're all scaled at spectral acceleration 0.17, as I promised. If they weren't scaled, we'd see a little cloud of results here, but the scaling reduces the dispersion. And these are the drifts, and they measure from about 2 to 3%. Then we took one of our so-called random sets, or A sets, as we call them, arbitrary sets, of 10 records, selected at random from the computer catalog of records, and random at their median spectral acceleration, which was 0.1. They're clearly generally smaller magnitudes, generally larger distances, they're generally weaker records, so it's not surprising that they are not themselves as strong as this large magnitude 7 close distance set that is our target set. So they give displacements down here about half as large, but then we took these records and simply scaled them up to 0.17, scaled them all by about a factor of 1.5. And the blue dots are the same result, same records then, scaled up, and those are the displacements that we get. And these two lines are the two medians. So clearly the median response from the real records and the median response from the wrong records scaled to the right spectral acceleration is virtually identical, well within the statistical error band. Here we've done exactly the same thing. We've just decreased the yield strength of the oscillator so that it has ductilities closer to 6, more severe nonlinear behavior. Exactly the same thing. The X's are the real records, the target records, magnitude 7 close distance records. The blue records are the ones we chose before arbitrarily or randomly, and we simply scaled them up to this same spectral acceleration as the stronger records. The medians are within a few percent of each other. I'm sorry, this slide, I couldn't figure out how to make this slide better. I will in the future. What we have here are different sets, A1, 2, 3, 4, 5, of 10 randomly selected records. The case we just looked at was A3. This is the case we looked at. This is the sample size 10. Each of these first 5 groups here are sample size 10. This is the ratio of the medians, of the median response from the random set to the median response of the target set. And you can see there they run 106, 113, 106, 109. 1 is comparatively large, 127. Over here is a standard error of estimation of this ratio under the null hypothesis that the ratio is 1. So this says 0.1, well, the case we just looked at, the ratio is 0.113 with the standard error of estimation of 0.136. Clearly, this 113 is within one standard error. We would conclude as statisticians that we can accept the null hypothesis that the ratio is 1. Or more intelligently, we could say that we get the same responses from the random sets of records as we do from the target sets of records. And that's virtually the same throughout here. The only case where this is 127 versus 17, that's a case of maybe 1.5 sigma. It's beginning to stretch the acceptance limit, perhaps, but it's only one of these cases. If we now combine cases, say 1 and 2, 3 and 4, to make sample sizes of 20, again, the limits are very close to 1. The ratios of median response of arbitrary sets to target set. The standard errors go down because we've increased the sample size. Here's groups of 30, and so the standard errors go down, making our tests more powerful statistically. but again, the conclusions are very much the same. We can get the same answers with records of rather arbitrary magnitude and distances. Then we've taken some other sets to kind of stretch this hypothesis. For example, we've taken all the strongest records, that is, the ones with the largest recorded spectral acceleration, weakest set, to take all the records from one event, take different low magnitudes, etc. And just to look quickly at some of those, here are the weakest, maybe the highest records. One had the highest spectral accelerations. They actually gave one of the smaller ratios, somewhat less than one. Not the only case here that were here, many records, all the records 8 taken from the Loma Prieta event, 112, all from the Imperial Valley event, 129, the Northridge event, 0.88, all very close to 1. Here are the lowest magnitudes. They're all around between 6.2, 6.3, 115. These happen to, well, I won't discuss these. These are the ones that our seismologist, Paul Somerville, working for the PEER project, chose for us to use when studying structures in Los Angeles. They actually give the ratios somewhat distant to 1. All the records from soil type C, 104. All from soil type D, 115. The point is this ratio is almost always 1. You can see the case that's actually 3 sigma out, here are the standard errors of estimation again, is actually when we take the records with the lowest strings. 10 records with the lowest string. And a couple of these cases that Dr. Somerville showed. I'm sure why it's supposed to be the case. So looking at this one test case, it says suggesting then that if we scale records this way, which is a natural way, I believe, the medium displacements are apparently effectively independent of the record set used. And that's, as I said, that's a rather heretical conclusion to come to in the face of all the care and effort that's taken to selecting records. There are a number of provisos here. First, we haven't looked at very many cases. This was a quick study by a student to help me prepare a lecture. He's looking at some more periods, some more backbones on the oscillators, etc. The number of provisos. One shouldn't go too very small with these magnitudes, or you will change spectral shapes significantly and perhaps make more difference. Let's say below 6 or below 5.75. We avoided all records with directivity or shallow soil, soft soil, or basin edge effects. So those are special cases that may require more care. We'll come back to the directivity, your source issue, a bit later. We've also done the same thing with a nonlinear structure. This is a model of the Van Nuys Holiday Inn, a famous structure that's been beaten by many serious earthquakes. It's an older reinforced concrete frame structure. We took the same scenario set, and we took one of these random sets, the same one we looked at before. These are the maximum story drifts, 0056, 003. These are correspond to ductilities. It's hard to measure ductility of reinforced concrete, but ductility of 2 to 3 in the worst story. Again, ratio very close to 1, well within the standard error of estimation. Okay, so those are some examples of direct comparisons. We have some indirect ways to look at this test this same question. And the question is, in statistical terms, once we know the intensity level as measured by spectral acceleration, do other properties of the record, such as its causative source, its magnitude, its distance, do they seem to have important effects on nonlinear structural response? Another way to solve that problem, looking at it more formally as probabilists or statisticians, is to say what we're trying to calculate ultimately is the annual probability that the drift, read that as drift, it's engineering demand parameter, the annual probability exceeds level X. We can solve that with a complicated total probability theorem expansion by saying, well, let me calculate the probability it exceeds X when I know the level of the intensity measure, say spectral acceleration, first bone. I know the magnitude, I know the distance, I know anything else here, like faulting style, etc. And then I can multiply that conditional probability by the conditional probability of I m intensity measured given magnitude distance, and multiply by the likelihood of getting events with given magnitudes, given distances, etc. So this is a two-step total probability theory expansion. What does that buy us? Well, the question is, under what circumstances can I take this term, which says the conditional probability of exceeding drift X given the intensity measure, the magnitude, and distance, and replace it. When can I simplify that and replace this by this much simpler expression? Well, I can do that if there is what we call conditional independence. That is, if this term up here, which is in general, according to total probability theorem, I must maintain dependence on intensity measure, magnitude, distance, etc. If I can drop the dependence on magnitude, distance, and other properties of the record, other than its intensity, and if that's true, if that equality is true, that is to say that the demand, or pardon me, the drift is independent of magnitude, distance, faulting, style, etc., provided you give me the intensity. If that's true for all magnitudes, all distances, etc., I can replace this complicated relationship by this one, which says I only need to analyze records once I know the intensity measure. I can forget which magnitude and distance and other property came from. So we change the problem to this indirect approach of studying this question of independence, conditional independence of predictions of drift. Once we've conditioned on intensity, we study their conditional dependence on other properties such as magnitude. Here's a typical result. Here's that same intense Van Nuys Holiday Inn, older reinforced concrete frame. We've used a degrading strength model due to Jose Pinchera. Has a natural period of about 8 seconds roughly. We've used 60 records. Notice the records are not scaled. I think I even said that here. Yes. No scaling. That's for those people who find scaling unattractive. So here we have the results of some 60 nonlinear analyses of this structure. It's a 7-story, 3-bay concrete frame. So these are the spectral accelerations of the records. These are the maximum story drifts observed, ranging from 1/10 to 1 to 2 or 3%. And here's a line fit on log paper. So it gives us a form that says the median drift is a constant A times spectral acceleration to the power B. Notice the power B is approximately 1, so we could have obtained the same thing by just a straight line on arithmetic. So that's over a very broad range of records, 5.3 to 7.3. Just a repetition of that statement. So the question is, can we look at those, at that kinds of results and argue that there is conditional independence of what magnitude? We're going to use a simple, what we call first order test. We're just going to look at whether magnitude and distance affect median responses. We're going to do this by looking at whether the dependence seems to be, on magnitude, seems to be effectively 0. So what we do is we go in 2 steps. Remember, we want to fix spectral acceleration. We want to condition on spectral acceleration. So we look at spectral acceleration. We take each data point, for example, that one, and we look at the residual. How far is the drift away from the predicted value, the straight line, for that particular record? There would be a positive residual. Here's a negative residual. Then we run a second regression of magnitude on spectral acceleration. So for each one of those data points, corresponding data point down here, we find this, that it's spectral acceleration, and so we find the corresponding data point down here. The residual here says, for that spectral acceleration, here's the magnitude I expect, or the average magnitude for that spectral acceleration. Here's the residual, here's a negative residual, here's a positive residual. So for that data point, for example, we look at this negative residual, this positive residual, we plot them data point by data point, and we get a plot of the residuals of drift as opposed to the residuals of magnitude. Why these residuals? Because we want to condition on spectral acceleration. We want to take spectral acceleration out of the problem and say, is there any apparent dependence of the drift, the displacement, on the magnitude of the earthquake that caused the record? The fact that this line is very flat suggests there's very little dependence of displacement on magnitude once you know the spectral acceleration. We test that statistically by looking at the slope here, the slope B. I'm sorry, that's probably hard for you to see. The slope B of the line fit to the residual plot is 0.14. The standard error of estimating that is 0.8, I believe. We're given what a statistician calls a p-value of about 5%. It would be, that's a one-sided test. A two-sided test would be even larger. So if that number is fairly large, it says this is really almost a statistically insignificant trend. Large means 5, 0.05, 0.1 or more. But you can see the trend is very weak. Even if you believe the trend is there, even if you believe that that is the real line that you would get if you had a sample size not of 60 but of 6,000, the dependence is quite weak. This B is on a log-log plot or a log magnitude plot, so it says the displacement changes like e to the power, magnitude to the power 0.14. So a 0.5 change, half a unit error, let's say, magnitude, means perhaps an e to the 0.14, or perhaps a 7% change in drift. So big changes in magnitude away from the important value, if you miss in estimating the magnitudes, do not mean large changes, even if that line is real and not just a statistical origination. So the conclusion of this particular structure is, again, there's no significant dependence of drift on magnitude, one side conditioned on spectral acceleration. That tells me when selecting records, I need not be very careful about selecting records to have correct magnitudes, correct meaning consistent with the site threat. Why am I only focusing on magnitude? Well, of all of the variables we've looked at, magnitude, distance, faulting style, magnitude is the one that may be a challenge.